most critical hour of a blast furnace is its first ignition. So today we will focus on silicon control, slag fluidity and key signals that show the furnace is becoming stable. So this is going to be a very important presentations. So next slide, which is especially about the thermal awakening. So during blow-in, we use very high thermal input to dry the burden and heat the hearth quickly. This creates high silicon, so we must manage the chemistry carefully from the start only. We rely on two data streams, live telemetry and lab analysis. One tells us what is happening now and the other explains why it is happening. So both are to be correlated perfectly to diagnose the things properly. We begin with a very high coke rate to secure hearth heat and dry the burden. Then we cut it aggressively to control silicon and avoid excessive fuel cost. Because if we delay in taking this prompt action, automatically our logistic will become handicapped and slowly the other running furnaces will be also paralyzed. Now at startup, lower basicity slag is safer always. This we have to aid in memory during revival of the furnace from blow-in. And lower basicity slag is safer because it stays more fluid at low temperature. If we push for high quality slag too early, we risk the freezing situation, and our system may hamper badly. Our revival time may be also prolonged. So high silicon is expected at blow-in, but it must fall quickly. If it stay too high, hot metal handling becomes difficult and plant logistic also suffer, as we have talked. And the most biggest problem is the our cast house will be paralyzed. Our mechanical equipments will be also damaged drastically. Our castables, our troughs are going to also damage severely. So we must have to bring down our silicon in a very justified manner. So as far the flame temperature is concerned, we must have to control as for the slag stability, liquidus temperature and final separation. So if heat drop too early, the whole process become unstable. So whatever the things is to be done, we must have to consider the sensitivity and the reflex action, the thermal control rules of the factors in mind. So the initial coke buffer protect the hearth heat, but it must burn down at the right pace. Too fast cause chilling and too slow keep silicon high. So we need to optimize the minimal burning intensity rate, and that gives us our good solution. So as for the high silicon is not a raw material failure, it is basically an engineered result of a heavy initial coke rate used to dry the burden safely. So try to understand that what is the consequences of the higher silicon. So if our understanding is very clear, we can bring we can control the situation within a short stipulated time, and which will better, as we have discussed already, that it will better for everything like logistic and etc. So we must keep the slag basicity in the safe range until silicon is under control. Raising basicity too early can freeze the slag, and it is difficult to take the thermal shock by the such type of slag. And especially when we are starting the furnace, such shock are pretty obvious because system is going to stabilize at that moment of time. So we need to architect or we need to engineer our slag in such a way that it can take a cushion or thermal shocks can sustain. So coming to the moisture and blast, as for the blast moisture and temperature, our main our main control lever for the silicon. So we use them carefully to reduce silicon without disturbing the furnace stability. As far the data continuity is concerned, a successful blow-in depends on seamless coordination between operation, automation, lab, and cast-house team. So, shift handover must protect process memory and decision continuity. So, all this brings your revival process faster and faster, early and early, with a minimal losses to the organization. As for the first cast are mainly diagnostic, not production driven, so their purpose is to confirm open thermal channel and proper hearth response. So this cast has to be viewed in from that point of view also by the operator. And as for the telemetry, anomalies are concerned when top temperatures become dynamic. It means the burden is drying and moving, and it's a sort of a wavy texture or a wavy curves. So at that moment, operators must react quickly to control the pressure and descent, and not try to normalize the furnace as quickly as possible. As for the final rule, uh, trust on the data is concerned. So we must have to avoid the premature chemistry correction and reduce the coke only when furnace is ready. So that is a very important line that each operator had to aid in memory before curtailing or correction in the fuel rate. So that is how we move from blowing to a stable production.